Researchers have made a discovery about the properties of water that could provide an exciting addendum to a phenomenon established over 2 centuries ago. The discovery also holds interesting possibilities for cooling devices and processes in industrial applications using only the basic properties of water. Their work was published in the journal Physical Review Fluids. Water can exist in 3 phases: a frozen solid, a liquid, and a gas. When heat is applied to a frozen solid, it becomes a liquid. When applied to the liquid, it becomes vapor. This elementary principle is familiar to anyone who has observed a glass of iced tea on a hot day or boiled a pot of water to make spaghetti. When the heat source is hot enough, the water's behavior changes dramatically. A water droplet deposited onto an aluminum plate heated to 150 degrees Celsius or above will no longer boil. Instead, the vapor that forms when the droplet approaches the surface will become trapped beneath the droplet, creating a cushion that prevents the liquid from making direct contact with the surface. The trapped vapor causes the liquid to levitate, sliding around the heated surface like an air hockey puck. This phenomenon is known as the Leidenfrost effect, named for the German doctor and theologian who first described it in a 1751 publication. This commonly accepted scientific principle applies to water as a liquid floating on a bed of vapor. The research team found themselves wondering, could ice perform in the same way? There are so many papers out there about levitating liquid. The researchers wanted to ask the question about levitating ice. They had the question of whether or not it was possible to have a 3-phase Leidenfrost effect with solid, liquid, and vapor. Curiosity sparked the first investigation some 5 years ago in the form of a research project. What they observed was fascinating. Even when the aluminum was heated above 150 degrees Celsius, the ice did not levitate on vapor as liquid does. The team continued raising the temperature, observing the behavior of the ice as the heat increased. What they found was that the threshold for levitation was dramatically higher, 550 degrees Celsius rather than 150 degrees Celsius. Up until that threshold, the meltwater beneath the ice continued to boil in direct contact with the surface rather than exhibit the Leidenfrost effect. What was going on underneath the ice that prolonged the boiling? The answer turned out to be the temperature differential in the meltwater layer beneath the ice. The meltwater layer has 2 different extremes. Its bottom is boiling, which fixes the temperature at above 100 degrees Celsius, but its top is adhered to the remaining ice, which fixes it at about 0 degrees Celsius. The research revealed that the maintenance of this extreme temperature differential consumes most of the surface's heat, explaining why levitation was more difficult for ice. The elevated temperature of 550 degrees Celsius for the icy Leidenfrost effect is practically important. Boiling water is optimally transporting heat away from the substrate, which is why you feel ample heat rising from the pot of water that is boiling, but not from a pot of water that is merely hot. This means that the difficulty in levitating ice is actually a good thing, as the larger temperature window for boiling will result in better heat transfer compared to using a liquid alone. Heat transfer comes most into play for cooling off things like computer servers or car engines. It requires a substance or mechanism that can move energy away from a hot surface, redistributing heat quickly to reduce the wear and tear on metal parts. In nuclear power plants, the application of ice to induce rapid cooling could become an easily deployed emergency measure if power fails, or a regular practice for servicing power plant parts. There are also potential applications for metallurgy. To produce alloys, it is necessary to quench the heat from metals that have been shaped in a narrow window of time, making the metal stronger and less brittle. If ice were applied, it would allow heat to be offloaded rapidly through the 3 water phases, quickly cooling the metal. The researcher also foresees a potential for applications in firefighting. We could imagine having a specially made hose that is spraying ice chips as opposed to a jet of water.